Gonzalez Albarillo from the Don Mariano Marcos Memorial State University, La Union, Philippines, and I am here today to present to you our research entitled Impact of Automatic Image Classification and Blind Deconvolution in Improving Text Detection Performance of the Graph Algorithm. Text, being one of humanity's most prominent inventions, has played a significant role in human life since ancient times. With the rise and development of deep learning, computer vision has been tremendously transformed and reshaped. A wave of change brought about by deep learning has unavoidably influenced a specific area of research in computer vision and document analysis called text detection. The community has recently experienced significant improvements in thinking approach and performance. Over the years, syntax detection has been a popular topic in the field of computer vision. It aims to localize text instances through bounding boxes. It is considered as a difficult problem and remains to be challenging due to the diversity of text patterns and complexities of scenes. Text pattern diversities and complexities include arbitrary fonts and sizes, and different scales and forms, cluttered image background, and variation of light conditioning. The task in detecting text in scene images has gained considerable attention as indicated by the robust reading competition which was organized in 2011. One of the challenges in the said competition is the focus syntax. It has three editions such as the ICDAR 2011, the ICDAR 2013, and the ICDAR 2015. The ICDAR 2013 edition is the definitive one in text detection. Furthermore, the said competition has three performance metrics such as the ICDAR 2013, the dataset, and the intersection over union, with each method having its own ranking of top-performing algorithms. As the best H-mean scores in the three metrics indicate, it is the IOU metric that has the most room for improvement. Hence, this study is focused on exploring techniques that can bring forth such improvement on the IOU. One of the algorithms that is able to handle complex scenarios well is the craft algorithm, which ranked 6th. The performance of the proposed method is evaluated through the use of intersection over union. The IOU quantifies how well the predicted bounding boxes overlap with the ground truth boxes. The higher IOU threshold requires the better overlap. An IOU score which is greater than 0.5 is considered to be a good prediction. Thus, it is an acceptable measure to decide whether the texts have been located. After computing the IOU, the precision, recall, and H-mean of the proposed method are also determined in order to evaluate its performance. The precision, recall, and H-mean are computed from the prediction to evaluate the IOU performance. H-mean refers to the harmonic mean of the precision and recall, and therefore takes into account both false positives and false negatives. One of the algorithms that is able to handle complex scenarios well is the character region awareness for text detection, also known as CRAF. We explored on CRAF because its code is available online, and its performance to the other evaluation metrics are also one of the top ranking since it ranked 4th and 3rd on ICDAR 2013 and dataset respectively. Craft is a text detector that localizes the individual character regions and then connects the detected characters to a text instance. It employs a convolutional neural network to generate the character region score, which is used to localize individual characters in an image, as well as the affinity score, which groups each character into a single instance. To compensate for the lack of character-level annotations, a weakly supervised learning framework was proposed. By exploiting character-level region awareness, text in various shapes are also easily represented. This research focused mainly on investigating the impact of automatic image classification and blind deconvolution as image pre-processing steps to further enhance the text detection performance of the craft algorithm. Specifically, this study determines the weakness of the craft algorithm with respect to syntax detection that can be improved on. Second is to develop an automated technique that can be used to reduce the impact of the identified weakness and thereby improve the performance of the graph algorithm. And lastly is to determine the impact of the proposed technique on the graph's algorithm performance. In conducting the study, we first identify and download appropriate datasets. Second, we review state-of-the-art algorithms performance on the dataset. Third, we replicate graph's performance on the dataset. Fourth, we segregate the images where graph algorithm is inaccurate. And lastly, we analyze some common property or properties in the segregated images. The International Conference on Document Analysis and Recognition 2013 or the ICDAR 2013 Focus Syntax Challenge 2 dataset was used. It is composed of 233 test images and 299 training images. Craft is a text detection method which effectively detects text areas by exploring each character and affinity between characters. Its primary objective is to locate individual characters in natural images. A deep neural network is trained to predict character regions as well as character affinity to cover a variety of text shapes in a bottom-up manner. Craft uses a VGG16-based fully convolutional neural network with batch normalization. Craft, like UNet, bypasses the connections during decoding and collects the low-level features. Herewith is the illustration of Craft's weakly supervised learning. In achieving character-level annotation from word-level annotation, the character split procedure is used. First, it grabs the word-level image. Second, it predicts the region score. Third, it applies watershed algorithm. Fourth, it gets the character bounding boxes. And lastly, it unwraps the character bounding boxes. Herewith is the source code of the Craft algorithm. Authors of the said algorithm were kind enough to share a copy of the source code available for download. The heart of the study is the experiments on improving Craft's performance. The goal is not just to bring improvement to the performance of Craft, but to actually make the improvement sufficiently big such that the proposed technique even outperforms the current state-of-the-art algorithms for text detection, including the current top-ranking SenseTime. This is quite a challenging task, especially since the text detection is a well-studied problem and many researchers have attempted to develop algorithms that perform very well on ICDAR 2013 dataset. In identifying the weakness in Craft, the main step done in this study was to secure a copy of the Craft algorithm and to run it against the ICDAR 2013 dataset. After confirming that the performance exactly matches what is published in the official Robust Reading Competition website, the dataset was partitioned into two, one consisting of images where Craft algorithm performs poorly and the other one consisting of images where Craft performs well. The following images show the detection performance of Craft algorithm on some clear images. It can be gleaned that the precision we call an H-mean garnered 100%, thus said to be a good prediction. Furthermore, the following images show the detection performance of the Craft algorithm on some blurry images. It can be gleaned that the detection performance of the Craft is poor, as it is evident by its precision of 33.32%, its recall of 50%, and its H-mean of 40%. Moreover, Craft's performance on image 16 yielded 0% in its precision, recall, and H-mean. Though Craft's performance is already commendable, it treats the images of ICDAR 2013 to be free from any blur or image distortion. Craft's detection performance to blurry images yielded poor results. It can be deduced that Craft's weakness is handling blurry instances, thus improving the blurry images can further improve Craft's detection performance. If humans who has blurry visions needs glasses in order to see and read words clearer, what if we remove blur in the images using the blurring method before implementing Craft? After identifying the weakness of the craft algorithm, we can now proceed to our research questions such as, how can the weakness be addressed algorithmically and thus bring an improvement in the performance of craft? And how does the proposed improved algorithm compare against the original craft algorithm and other state-of-the-art syntax detection algorithms? For our research questions 2 and 3, we first explore one or more deblurring techniques, including experimentation and parameters of the technique or techniques. Then we explore segregation of images in order to selectively apply deblurring only on segregated images. Afterwards, we run craft variant and compare IOU results. And lastly, we repeat the process until a variant is able to outperform the state-of-the-art SenseTime and satisfied with the results. What if all images were deblurred? Image deblurring plays an essential role in generating sharp and useful images. The unprecedented blur and distortion effects caused by camera and movements significantly affect the quality of the captured images. Thus, text deblurring plays an essential role in generating sharp and useful images. Blind deconvolution permits the recovery of target scene from a single or set of blurred images in the presence of a poorly determined or unknown point spread function or PSF. It targets recovering a sharp version of an input blurry image when the blur kernel and the latent image are assumed unknown, thus making it more challenging. Point spread function or PSF describes the degree to which an optical system blurs or spreads a point of light. It represents the Gaussian filter. In blind deconvolution, motion blur kernels and the latent image are alternatingly optimized in an iterative process. From the estimated latent image and the given blurred image, blur kernels are obtained. These kernels are then used to produce new estimated latent image by applying non-blind deconvolution to the given blurred image. This new estimated latent image is then used in the next iteration of the kernel estimation. Herewith is an example of an image which underwent blind deconvolution using 11, 12, 13, 21, 22, 23, 31, 32, and 33 PSFs. Furthermore, the image shows the analysis of reconstructed PSFs, which might help in guessing the right PSF value to be used in an image. The code segment restores the image by applying 1 pixel longer in each dimension, such as the X and Y, than the true PSF. The detected blurry images undergo blind deconvolution by applying one of several different PSFs, such as 11, 12, 13, 21, 22, 23, 31, 32, and 33. This study explores on the precise PSF values that will be applied to the blurred images in order to achieve an improved performance in text detection. Upon identifying the precise value to be applied on a given blurred image, the blurred image will then be subjected to text detection using the craft algorithm. This table shows the results of the initial experiment in which all the images in the datasets were subjected to blind deconvolution. As indicated in the table, we tried various PSFs. All entries in the table show performance that are each superior to that of standard graph. This verifies handling image blur is indeed the weakness in the craft algorithm. An updated ranking of the top-performing algorithms shows an impressive ranking of the proposed algorithm. The best results of using blind deconvolution as pre-processing step for craft was garnered when using a PSF of 1-2. Under this configuration, the proposed craft yielded an IOU-H mean of 93.37%, which is a marked improvement over the 91.42% IOU-H mean of the original craft. The performance is even better than that of the current second-ranked algorithm, which is TextMuseNet, which is only 93.11%. However, this is still a bit inferior to that of SenseTime, whose IOU-H mean stands at 93.62%. Herewith is an instance where BDCraft performs better than Craft. In the first image, It uses a Kraft algorithm and yielded 0% in all its precision, recall, and h-mean. Meanwhile, when applying BD-Kraft, it garnered a precision of 100%, a recall of 33.33%, and an h-mean of 50%. Another instance where BD-Kraft performs better than Kraft is shown in this image. In the first image, it has a precision of 80%, a recall of 100%, and an h-mean of 88% when applying Kraft algorithm. Meanwhile, when using BD-Kraft, it garnered 100% in all its precision, recall, and h-mean. On the other hand, there are also instances where Kraft performs better than BD-Kraft. In this particular image, when applying Kraft, it yielded a precision of 100%, a recall of 83.33%, and an h-mean of 90.90%. Meanwhile, when applying BD-Kraft, it only garnered a precision of 100%, a recall of 66.67%, and an h-mean of 80%. The performance of the Kraft algorithm decreases after applying blind deconvolution, as evident by this image. After applying blind deconvolution, the Kraft algorithm was able to detect possible text, thus affecting its precision. Due to the few instances when application of blind deconvolution to an image decreased the performance of Kraft, we therefore decide to explore separating non-blurry images from blurry images so that the deconvolution is applied only to the latter type. Our proposed method is illustrated by this flowchart. The syntax image will undergo blur or non-blur classification. If the image is of poor quality or blur, it will undergo image deblurring before it will proceed to text detection. Otherwise, if it is of good quality or non-blur, it will automatically undergo text detection. The input syntax image undergoes quality assessment by determining if the syntax image is of good quality or clear, or it is not. A scene image is said to be of poor quality when it is affected by blur or noise which may be caused by motion, camera shake, and lighting. In blurry and non-blurry classification, the syntax image is to be automatically classified whether it is blurry or a clear image using a certain threshold. It computes the Laplacian of the image and returns the focus measure, which is simply the variance of the Laplacian. If the focus measure is less than the supplied threshold, the image is considered as blurry, otherwise non-blurry. The blur detection can be done with a line of code which returns the average variance of the edges in the image. The higher the number, the sharper the image is. To automatically classify an image as either blurry or non-blurry, we simply compute this value for the input image and compare this against a predetermined threshold. The reason this method works is due to the definition of the Laplacian operator itself, which is used to measure the second derivative of an image. There is a wide spread of responses, both edge-like and non-edge-like representative of normal. In focus image, the image contains high variance. However, there is a tiny spread of responses if there is a very low variance, indicating there are very little edges in the image. It can be deduced that the more an image is blurred, the lesser the edges are. The set threshold is a crucial parameter to be tuned correctly. Applying too small threshold or too large values may lead to incorrect classification of images. To determine an appropriate threshold for our proposed algorithm, we experimented on several thresholds such as 30, 50, 80, 100, 150, and 200. Among these, threshold 100 yielded the best result. This is in consonance with the result of the published work of Pacheco in the year 2000 that a threshold 100 is a good threshold for a blurry or non-blurry classification. After assessing the input scene image, if the image has a focus measure higher than the supplied threshold 100, it is considered non-blurry and will undergo syntax detection using Kraft. Otherwise, the scene image will undergo another preprocessing step, which is blind deconvolution. In blurry or non-blurry classification, out of the 233 images in ICDAR 2013, 63 were classified as blurry while 170 were classified as non-blurry. Experimental results show that when applying blind deconvolution on detected blurry images only, the performance of craft has been improved in some PSF values such as 11, 12, 13, 21, 32, and 53. The best results was obtained on blind deconvolved images using the PSF 13. This garnered a 94.47% H-mean, which is better than that of the state-of-the-art SenseTime's H-mean result of 93.62%. There are also other PSF values that eventually yielded results also better than that of SenseTime's. It is in consonance with the idea that when the PSF is unknown, it may be possible to deduce it by systematically trying different possible PSFs and assessing whether the image has been improved. The final proposed algorithm is the BD graph. First, the syntax image will undergo blurry or non-blurry classification. Then, if the particular image is of poor quality or blurry, it will undergo blind deconvolution. Then, it will proceed to text detection. Otherwise, if the particular image is of good quality, meaning it is clear, it will probably proceed to text detection. The result of the currently proposed technique on ICDAR 2013 dataset outperformed the performance of the previous studies as reflected by its precision, recall, and H-mean. By combining said pre-processing steps with craft, the BD craft improves the performance of craft sufficiently to the point of besting even the SenseTime algorithm, which is the current state-of-the-art for syntax detection. In ICDAR 2013, BD craft garnered an H-mean of 94.47%, which is better than those of craft, which is 91.42%, and SenseTime, which is 93.62%. As to the conclusion, the weakness of craft algorithm is syntax detection in blurry images. The developed BD craft, a variant of the craft algorithm, improved craft's performance sufficiently to the point of besting even the SenseTime algorithm, which is the current state-of-the-art for syntax detection. As possibilities for further studies, it would be interesting to investigate which state-of-the-art algorithms for syntax detection would benefit also from the discussed input pre-processing techniques. It may also be good to investigate other pre-processing techniques that can be incorporated in text detection algorithms in general. Words are singularly the most powerful source available to humanity. Words have the ability to help, to heal, and to humble. Again, this is Clarisa Albarillo. Thank you very much.